Hello students, this is Miss Pooja Arun Mhatre, lecturer in Electronics and Telecommunication Department in Praveen Patil College of Diploma Engineering and Technology, Bhinder East. Today's topic is CND, chapter number 4, Data Link Layer, part 3. The learning course outcomes are error correction method. In that we will learn about the linear block code and Hamming code. First we will see what is error correction. Error correction, as name suggests, simply means the correction or a solving or fixing of errors. Error correction means correcting the errors, solving the error, fixing the errors, etc. So it simply means reconstruction and rehabilitation of original data that is error free. But error correction method is very costly and very hard. So in the digital world, the error correction can be done in two ways. First is the backward error correction and second one is the forward error correction. So error correction means we have to reconstruct the original data. So that can be a error free. For that we use two methods, backward error correction and forward error correction. First we will see the what is backward error correction. So when the receiver detects an error in the data received, it requests back the sender to retransmit the data. In backward error correction, when receiver detects an error, so it requests to the sender to retransmit the data. This is called a backward error correction. What is a forward error correction? When a receiver detects some error in the data received, it executes the error correcting code which helps it to auto recover and to correct some kinds of error. That means when the receiver receives the error or detect the error in received data, that time it executes the error correcting codes and auto recover the data. Linear block code. In the linear block code, the parity bits and message bits have a linear combination, which means that the resultant code word is the linear combination of any two code words. So let us consider some blocks of code which contains a k bits in each block. These bits are mapped with the blocks which has n bits in each block. So here n is greater than k. The transmitter adds a redundant bits which are n minus k. The ratio is k upon n is the code rate. So it is denoted by r and the value of r is greater than r is less than 1. So the n minus k bits added here, which is the parity bits. So parity bits helps the error detection and correction and also in locating the data. So in this data being transmitted, the leftmost bit of the code word is correspond to the message bits and the rightmost bit of the code word correspond to the parity bits. Here the diagram showing the structure of the code word. The left bit is a k bit and that is a message bit and right bit is a n minus k bits, that is a parity bits. What is systematic code? So any linear block code can be systematic code. That means any linear code be a systematic code until it altered. That means when a linear code alter, it become a systematic code. So an unaltered block code is called a systematic code. So any linear code can be systematic code until it is altered. So an unaltered block code is called as a systematic code. The following is the representation of structure of code according to their allocation. That means the left for the message bits and right for the parity bits. So if the message is not altered, then it is called a systematic code. It means the encryption of data should not change the data. The example of the linear block code is A bits are 6 comma 3. So there is a 6 comma 3 code, that is 2 raised to k is equals to 2 raised to 3 is equals to 8, and there are the n. N means first bit. 2 raised to n is equals to 2 raised to 6, that is equals to 64, that is 4 tuples in the v6 vector space. So message vectors are code of 0 to 8 and the code word is 0 to 8, that is in the 3 bits. The message vector is in the 3 bits and the code words is in the 6 bits. Hamming code. First we will see the history of the Hamming code. The Hamming code is a technique built by the R.W. Hamming to detect errors. So Hamming code should be applied to the data of the any length and uses the relationship between the data and redundancy bits. He worked on the problems of the error correction methods and developed an increasingly power array to algorithm called Hamming code. In 1950s, he published the Hamming code which widely used today in applications like ECC memory. So Hamming code is a linear code that is useful for the error detection up to 2 immediate bits errors. It is capable of single bit errors. So in this coding method, the source encodes the message by the inserting redundant bits within the message, and these redundant bits are extra bits that are generated and inserted at the specific positions. So in the message itself, to enable error detection and correction, when the destination receives the message, it performs the recalculations to detect errors and find bit position that has error. Applications of Hamming code. Here are some common applications of using Hamming codes. First one is the satellite, then computer memory, modems, cam, open connectors, shielded wire, embedded processor, etc. Advantages of Hamming code. The Hamming code method is effective on network where the data streams are given for the single bit errors. Hamming code not only provides the detection of bits error but also helps you to indent bit containing error so that it can be corrected. The ease of use of Hamming codes makes it best them suitable for use of computer memory and single error correction. Disadvantages of Hamming code. A single bit error detection and correction code. However, if multiple bits are founded error, then the outcome may result in the another bit which should be correct to be changed. This can cause the data to be further eroded. So Hamming code algorithm can solve only single bit issues. Encoding a message in Hamming code. The procedure used by the sender to encode the message encompasses the following steps. Step 1 is calculation of the number of redundant bits. Step 2 is positioning the redundant bits. And step 3 is calculating the values of each redundant bit. So once the redundant bits are embedded within the message, this sent to the user. So first step is calculation of the number of redundant bits. If the message contains a number of data bits or RR number of redundant bits are added to so that the MR is able to indicate at least M plus R plus 1 different states. So here M plus R indicate the location of the error in each of the M plus R bit position, and one additional state indicates no error. So since RR bits can indicate two RR states and two RR states must be least equal to the M plus R plus 1. Thus the following equation should hold 2R is greater than equal to M plus R plus 1. The second step is positioning the redundant bits. The R redundant bits placed at the bits position of power of 2, that is 1, 2, 4, 8, 16, etc. So they are referred in the rest of the text as a R1, R2, R3, R4 and so on. Step 3. Calculating the values of each redundant bit. The redundant bits are parity bits. A parity bit is an extra bit that makes the number of ones either even or odd. The two types of parity bits are even parity and odd parity. So even parity means here the total number of bits in the message is made even. The total number of ones bit in a message is made it even parity. And the odd parity means here the total number of ones in the message is made a odd parity. So each redundant bit R1 is calculated as a parity, generally even parity, based upon its bits position. It covers all bits position whose binary representation includes a 1 in the ith position except the position of R1. So thus R1 is a parity bits for all the data bits in position whose binary representation includes a 1 in the least significant position excluding 1, 3, 5, 7, 11, so on. So R2 is a parity bit for all the data bits in the position whose binary representation includes the 1 in the position 2 from right except 2, that means 3, 6, 7, 10, 11, and so on. So R3 is a parity bit for all the data bits in the position whose binary representation includes a 1 in position 3 from right except the 4 is 5 to 7, 12 to 15, 20 to 23, and so on. So decoding a message in Hamming code. Once receiver gets the incoming message, it performs the recalculation to detect errors and correct them. The steps of recalculations are: step 1 is calculation of the number of the redundant bits. Step 2 is positioning the redundant bits. Step 3 is a parity checking, and step 4 is a error detection and correction. Step 1, calculation of the number of redundant bit. Using the same formula as in encoding, the number of redundant bits are ascertained. So 2r is greater than equal to m plus r plus 1, where m is the number of data bits and r is the number of redundant bits. Decoding a message in Hamming code. Step 2, positioning the redundant bits. So the r redundant bits placed at bit position of the power of 2, that is 1, 2, 4, 8, 16, etc. Step 3, parity checking. Parity bits are calculated based upon the data bits and redundant bits using the same rules as during generation of C1, C2, C3, C4, etc. Thus C1 is equals to parity of 1, 3, 5, 7, 9, 11, and so on. C2 is a parity of 2, 3, 6, 7, 10, 11, and so on. And the C3 is a parity of 4 to 7, 12 to 15, 20 to 23, and so on. And the fourth step is error detection and correction. The decimal equivalent of the parity bits binary values is calculated. If it is 0, there is a no error. Otherwise, the decimal value gives the bit position which has error. For example, if C1, C2, C3, C4 is equal to 1001, so it implies that the data bit at the position 9 decimal equivalent of 1001 has an error. So bit is flipped to get the correct message. Hamming code for the error detection. As we go through the example of first step, so is to identify the bit position of the data, and all the bit position which are powers of 2 are marked as a parity bits, that is 1, 2, 4, 8, etc. The following image will help to visualize and receive a Hamming code of 7 bits. So D1, D6, D7, D6, D5, and D3 are the data bits, and P1, P2, P4 are the parity bits. So first we need to detect whether there are any errors in the received Hamming code. The Hamming step 1 for checking the parity bits P1 is check 1 and skip 1 method. which means starting from the P1 and then skip P2, then D3, then skip P4, then take D5, then skip D6 and then take D7. This way we will have the following bits, that is P1, D3, D5 and D7. As we can observe, the total number of bits are odd, so we will write the value of parity bit as P1 is equals to 1. This means error is there. Step 2. Check the P2, but while checking the P2, we will use the check 2 and skip 2 method, which will give you the following data bits. But remember, since we are checking for the P2, so we have to start our count from P2. P1 should not be considered. Then P2, D3, D6 and D7. As we can observe that the number of ones are even, so then we will write the value of P2 is equals to 0. This means there is no error. Step 3. Check for the P4, but while checking for P4, we will use the check for and skip for. Check for and skip for method, which will give the following data bits. But remember, since we are checking for the P4, so we have to start a count from P4. P1 and P2 should not be considered. So P4, D5, D6, D7. As we observe that the number of ones are odd, there will be write the value of P4 is equals to 1. This means the error is there. So from the above parity analysis, P1 and P4 are not equal to 0. So we can clearly say that the received Hamming code has a error. Since we found that the received code has an error, so now we must correct them. To correct the errors, use the following steps. That is P1, P2, P4, 101. Now we have to determine a decimal value of the error. Here the example of a bit word 1011 is to be transmitted. Construct the even parity 7-bit Hamming code for this data. Solution is the 7-bit Hamming code format is shown in the figure. There is given word, that is 1011. So P1, P2, P4, then D3 is 1, D4, D5 is 1, D6 is 0 and D7 is 1. So decide the P1. P1 is set, the parity of bits is P1, and D3, D5 and D7. As the D5, D7, D5, D3 is equals to 1, 1, 1. We have to set P1 is equals to 1 in order to have the even parity. So P1 is 1, have the even parity. Then decide P2. P2 set to have the even parity, the P2, D3, D6, D7. What the D3, D6, D7 is equals to 101. Hence set to P2 is equals to 0. So P2 is equals to 0 have a even parity of P2, P3, P6, P7. Decide P4. P4 is said to have a even parity for P4, P5, P6, P7. But D5, D7, D6, D7 is equals to 101. Hence P4 set to the 0. So 100, 1010101 is the complete code word, and the P4 is equals to 0 to have a even parity of P4, P5, P6 and P7. The 7-bit heaven, another example is a 7-bit even parity Hamming code is received as a 1110101. What is the correct code? We will check for the received code word is 1110101. So we will set the number of 1 to 7. So check the bit for the 4, 5, 6, 7, that is have a odd parity. So P4 is equals to 1, that is have a error. Check for the 2, 3, 6, 7 which have a odd parity. That means P2 is equals to 1 and hence error is occur. Check the bits for the 1, 3, 5, 7, that is have a even parity. That means P1 is equals to 0, hence there is a no error. So error code word E is equals to 110, P4, P2 and P1. So decimal equivalent of 110 is equals to 6 of 10. Decimal number is 6. The error is occur over there. The 6 bits in receive code word is incorrect, so invert it and correct the code word is 1 to 0. The sixth position is converted, that is called a inverted bit. In a particular system, the data received was a 1011010. Using 7-bit odd parity Hamming code, determine the corrected code. The received code word is 10111010. Check the bit for 4, 5, 6, 7, that is 1101, which have a odd parity, that is total number of ones is odd, so no error. P4 is equals to 0. Check the bit 2, 3, 6, 7, 1001, even parity, so error is equals to P2 is equals to 1. Check bit is 13570011, even parity, so error is occur, P1 is equals to 1. So error word is 011, P4, P2, P1, which is coded is 011. So decimal equivalent of E is equals to decimal number 3. The error is occur at the position of 3. So inverted bit is 1 at the third position. So data bits is 1011 have to be transmitted and construct the odd parity 7-bit Hamming code for the given data. So Hamming code word is 101 P4 1 P2 P1. There is a only data bit. There are no parity bits. So parity bits have to be calculated as, check the bit as 1357 for P1. 357 is 111 odd parity, that means P1 is equals to 0. Check the bits for 2361 for deciding P2. 367 is equals to 101 even parity, so P2 is equals to 1. Check bits for the P4. 4567 for deciding P4. So 567 is equals to 101 even parity. So P4 is 1. So required code for the with odd parity as follows: 1011110. Thank you.